some kit, but it's all surface mounted. You'll see a picture of it coming up, and it would be way more than the average ham kit builder could build. And it all started with a QEX article that Tom did for the ARRL, which I guess that was in January, February of 2009. And to have something that, covered, as you see here, 1 kilohertz to 1.3 gigahertz that, hams could use was quite the novel thing. But these things weren't cheap. So I think I paid around $450 for mine back 8 or 10 years ago, which was, a fair amount of money. But, at the time, I think the MFJs were going for like 250 or something. And so I decided to make the extra cost investment and pick one up. So this is what it looks like on the inside. As you can see, it's a very high density surface mount stuff. So not something that the average ham could build for sure in kit form. And let's talk a little bit about, what do we mean when we say it's a vector network analyzer? Well, when we talk about vectors from a mathematical sense, we're talking about something that we can measure and not only determine what its magnitude is or what its strength is, but also determine what its phase relationship is to other things. And we know that impedance, which is the AC form of resistance, is what's called in math terms a complex number. It has what's called a resistance portion and a reactance portion, and so if you had an impedance in that top right diagram, if you had an impedance of R plus JX of 4 plus J5, then on a graph, that's how you would represent it. The vector is the thing that's shown in purple, but that vector has a length to it, but it also, you see, it has an angle to it respective to the axis. And in impedance terminology, the horizontal axis is the resistance axis, and then the vertical axis is the reactance axis, with the positive side going up being the inductive reactance, X of L, and the negative side is the capacitive reactance going down. So if you had an impedance of 4 minus JX, then it would be an arrow going down to the right with a R of 4 and a J of minus 5. And that, in mathematical terms, so that's what's called Cartesian coordinates, where you have the R and X. It can be also shown in what's called polar form, where you have a magnitude Z, which is the length of the arrow, and then some angle relative to the R axis. So let's talk about waves and things here and what it is that we're really trying to do. And you can think of measuring RF circuitry similar to optics and a lens. If we have a lens and we provide an optical signal to one side of the lens, then a certain amount of that optical signal will get transmitted through the lens and appear out the other side. Some part of that optical signal will be reflected off the surface of the lens and get reflected back. And that same exact kind of thing happens with RF circuits. We have our device under test. In this case, this would be known as a two-port network because it has two connectors, an input and an output. We supply an incident signal to the input. Not all of that signal gets accepted by the network. Some of that signal gets reflected back, and then some of that signal goes through the network, transmitted through the network, and comes out of the other port too. And we do this because with low frequency circuits, like at audio levels and very low frequencies, with a circuit, we can actually go in there and we can measure, voltages and currents and put voltmeters and oscilloscopes and things into our circuits and do all the things we need to do to measure and characterize the circuits. But when you get into RF circuits, primarily once you start getting into much higher frequency RF circuits, you can't do that. As soon as you go in there and try to probe or measure things, you disturb the circuit, sometimes to the point where the circuit no longer works. So the only thing we can do then is, from an RF point of view, where things are relatively matched to the characteristic impedance of the circuit, we can measure these RF parameters of the through forward power and the reflected power. And these things are referred to in engineering circles as what's called S parameters, or scattering parameters. And this is another picture of if we have a two-port network. Now, what would this two-port network be from a ham point of view? Well, it might be a piece of transmission line, a phasing line. It could be a filter. It could be a RF amplifier. It could be, various things like that. Or it could be a one-port network, like it could be some sort of a dummy load. It could be a antenna, different things of that nature. So in engineering circles, they would refer to the vector network analyzer as what's called a two-port vector network analyzer. And typically you hear things talked about S parameter S11. That's just the reflected signal off of port 1. The way the S parameters work is the first number stands for the port where the signal is being applied, and the second number stands for, the first number is the port where the signal is being measured, and the second number applies to the port where the signal is being applied. So S11 would be the signal measured at port 1 from the signal provided at port 1. So it's the signal reflected from port 1. And S21 would be the signal measured at port 2 from the signal applied at port 1. So the way the vector network analyzer works is there's these things very similar to the directional bridge that you saw, or the reflectometer that you saw in the MFJ unit, but at higher frequencies, they are typically either magnetic units or strip line units, and they're called a directional bridge or a directional coupler. And what they do is they separate the incident and forward power, and they're usually coaxial in nature, and they can be screwed right onto the connectors of the device under test. And then the incident, the reflected, and the transmitted or through power can be measured. And just like the voltages that we measured in the MFJ unit, you would measure these signals and they would go to a receiver and then to a processor and do all the appropriate mathematics to get the desired thing that you're looking for. We'll go into a little bit more information. But the thing to be aware of here is, unlike the MFJ 259B, where they took that RF signal, they rectified it and created a voltage and just are looking at the strength of the signal. Here, they're actually taking the signal, they're running it into a receiver, very similar to a ham receiver. That receiver would down-convert the signal to a lower frequency so that it could be either sent through an IF strip, like in the old, superheterodyne, or the superheterodyne receivers that we hams are familiar with, and then over to a detector and a processor. But you're actually, with the vector network analyzer, you're preserving the actual phase relationship between the incident, reflected, and transmitted signal. You're no longer just looking at the magnitude voltage, but you're actually looking at the sine wave signals, and so you know the phase reference between all those three. So one of the things that we have to do with a vector network analyzer in order to get precise measurements is we have to calibrate the vector network analyzer, because with all these circuitries, the directional couplers and the detectors and the IF strip and all that stuff, there's errors associated with all that measurement equipment. And in order to get accurate measurements for the device under test, we have to take those errors out. And typically, with any network measurement like this, there are 6 errors that come into play. One is the directivity of the couplers, crosstalk between the input and output ports, the tracking of the signals, both the forward signal, the transmission, and the reflection signal. Those signals vary with frequency that when they're being detected. And then the device under test is not a perfect match, neither the input port or the output port. So there's mismatch between the instrument and the port on the device under test, and the source mismatch and load mismatch cause errors. And so there's 6 terms in the forward direction and 6 terms in the reverse direction that need to be characterized. And the way that this is done with a network analyzer is we do what's called a SOLT calibration. And SOLT stands for short, open, load, and through cal. And so you'll go through a sequence, and so on port 1 of the analyzer there, where it's connected to the left port on the device under test, you'll go through a sequence where you'll put on a short, you'll put on an open, and you'll put on a load. And so these are actually, metrology grade reference devices that are as close to a perfect short, a perfect RF open, and a perfect 50 ohm load as one can get. And knowing what a perfect short, open, and load should represent from a measurement point of view, the firmware or the software in the vector network analyzer measures all those parameters and calculates the difference between what it measured and what a perfect short or open or load should be. And it stores all those little error constants, those are called error vectors. And it does this for every frequency. As you sweep a network analyzer along, it it sweeps from a start to a stop frequency, and it digitizes that sweep maybe into 1,000 points or 2,000 points. And for every frequency point, when you're doing the calibration, it stores error numbers for all these 12 terms. So it does the same thing for the other port, and then eventually you hook port 1 to port 2 of the network analyzer with a cable. You take the device under test out, you put a cable, and that's the through connection. And it crunches all of that, and it saves all that data into what's called a calibration file. So then when you do a measurement, it takes the measured value and knows what frequency it's at and so forth, and it goes and looks up those error numbers, and it corrects the measurement that you're taking by the error numbers because it knows how much the error there is. And then what it displays to you is the corrected number where they've taken out the error in the measurement device, and it gives you the actual, as true as can be, measurement of what is you're looking at either port 1 or port 2 of the device under test. And this is just a what's called a flow model of how those S parameters work. The mathematical representation of how the different S parameters are related to the incident wave A1 and the reflected wave B1 from port 1, and the incident wave A2 on port 2 and the reflected wave B2 on port 2. So the basic way that we would use this vector network analyzer is we would take our device and we would connect it up to the ports of the analyzer. If we had a 2-port device, then we would connect it up as such, one port to the TX out and the other port to the TX in. If we were measuring a single port device like an antenna, we would just connect the antenna up to the TX out and leave the RX in port open. If we were measuring actually measuring a coax transmission line or a filter or something, then we would connect it up to the 2 ports. This is a screenshot of I believe this is a notch filter that Tom measured. Oh no, I'm sorry. This was a bandpass filter that Tom measured. This is a filter in the 145 megahertz range, a 2-meter bandpass filter. And what you see this is an actual what you see on the software screen for the vector network analyzer. The blue trace is the return loss, and the red trace is actually the SWR. And so you can see he's got two markers set up there, one at 144 and one at 146 megahertz, showing an SWR of 1.03 and 1.04. So very good match. And the return loss is minus 38 and minus 33 dB. So, it's like 1/1000th of the signal that's being put into the port is being reflected back. So it's a very good match, obviously. And so now this same filter, this is what the through connection, or the S parameter S21. So now you're measuring how the filter works. You're putting a signal in on port 1, and you're measuring the output of port 2, the B2 there shown up in the top. And so you see the typical band pass response shown here. The center of the filter, which is showing by marker 4 there, is at 145.2 megahertz. The insertion loss of the filter is only 0.3 dB, which is very good. And then he's showing the markers 2 and 3 are what's known as the 3 dB down points, and the frequency between those two markers typically is what's referred to as the 3 dB down bandwidth. And in this case, the bandwidth of the filter is 17.98 megahertz. So as you can see, you can measure, get some very sophisticated measurements, very accurate measurements of filters, setting up things like the cans in a repeater system. Having one of these network analyzers makes setting one of those things up much easier than trying to do it with other methods. So some of the things that we can measure with the vector network analyzer, obviously, is if you have an antenna, which is a one-port network, you can measure the antenna impedance, you can measure the VSWR and the return loss. If you have a two-port network like a cable, you can measure the cable insertion loss. Because this is a vector network analyzer, you can actually measure the electrical length of the cable, because, or remember, all the signals you're measuring, you not only know the strength of the signal, but you also know the phase of the signal. So you could compare the phase of the signal going into the cable and the phase of the signal coming out of the cable, and actually know what the electrical length of the cable. If you're trying to do like phase verticals or something like that, where you need, precise phasing lines, then having something like this is, makes that very easy. You can make, quarter wave, half wave, whatever lines at your particular frequency. From a 2-point, like I said, cables, filters, amplifiers, you can measure the input impedance, output impedance of an amplifier, as well as the gain and or the isolation going backwards into the amplifier. And you can also use it as a fixed level signal gen, because you can take the synthesizer output inside it and just feed it out. So here's what the block diagram of the vector network analyzer looks like. It's very similar to the MFJ, but like I say, so you have that directional bridge thing going on there. But the one thing that's different here is the RF signals coming off of the bridge go into down converters or mixers. That's what's shown by the 3 circles there with the X's in them, M1, M2, and M3. And a mixer is just like the mixer inside your superhet. It down converts the RF signal to a lower frequency, and in this case, they're mixing the RF signal right down to audio, and they're using the sound card inside of the computer, the stereo sound card, and they're providing those audio signals to the right channel and the left channel of the audio sound card. And then all the processing for all of this measurement is done in the PC. There's no processing of the data done within the analyzer itself. It's all done in software in the PC. So how this works, we'll go through a similar thing. So you have 2 direct digital synthesizers. One is the local oscillator signal, and the other one is the RF measurement signal. And both of those direct digital synthesizer are crystal controlled by a master crystal oscillator. That's the XO block in the middle. So first off, a LO signal is applied to mixer number 1. An LO signal is also applied to mixer number 2. Then we have an RF signal, which is the signal that you're trying to measure at, is supplied to mixer number 1. That RF signal then gets mixed with the LO, and an audio signal gets sent to the right audio channel as a reference of the signal that you're putting into the measurement network. The RF signal then also gets applied to the directional bridge or detector. That signal then goes out of the transmit port and would go to the device under test. In this case, if you had an antenna connected to it, it would go out to the antenna. And then the reflected signal that comes back off of the bridge, coming back from the antenna on port 1, would go off of the bridge up to mixer number 1. Mixer number 1 would down convert the measured signal, reflected signal, and bring it down to audio, and that would get applied to the left channel of the sound card within the PC. And then the PC would take those two signals, the reference signal and the reflected signal, and it would go through and calculate, the SWR and all the things that it needs to do. But remember, all of these signals are not only, they're real sine wave signals, so not only can you calculate the strength of the signal, but you can also calculate the phase of the signal. If you were doing a transmission measurement, like on a coax cable or an amplifier or a filter or something, then you'd have a similar process as to what we were talking about before. You still have that reference signal, but now also a local oscillator would be sent to mixer number 3. The RF signal would be sent to the directional bridge. The signal would come out the transmit port, but now you have a unit under test connected between the transmit and the receive port. So the output of your device under test, let's say it's a filter, you have a signal going into the filter, then a signal coming out. That output signal would go into the RX port, into mixer number 3. Mixer number 3 would down convert it. Mode control would switch that switch over now to the RX channel, and the signal would be measured now in the left channel would be the through signal and not the reflected. And once again, the software would do all the calculations, and it could measure the insertion loss of the filter. Remember that bandpass plot that we showed. Now remember, while this is going on, this is happening for every frequency. As this thing is sweeping across, these direct digital synthesizers are sweeping across those 1,000 or 2,000 points from start to stop. And at every frequency, it's taking the measurements. It's using that error-corrected value that it got from the short open load through cal, correcting the measurements, and then supplying that data to the output. So there's a lot of stuff going on in the software here. And so, there's all kinds of plots that you can get. Not only can you get, regular, plots, but you can do Smith charts. There's all kinds of things that you can do. It's very, very exhaustive data output. The same type of data output you see with this software is what I see on, professional network analyzers that, cost many hundreds of thousands of bucks, same type of information. So they put a lot of work into to developing the software for this. It even has a spectrum analyzer mode where you can put it into a mode where you can use it as a spectrum analyzer, and you can measure what type of spectrum you have. I mean, it doesn't have huge dynamic range like a real professional spectrum analyzer would have, but it's not too bad. And then once you get the data into the system, now you have all this data, you can do all kinds of things with it. And one of the things you can do is you have all this data, this RF data in what's called the frequency domain. Because it's a vector, and you have not only the magnitude, but you have the phase information. All of this data is represented as complex numbers, R plus JX, inside the computer system software. You can do what's called a fast Fourier transform and convert from the frequency domain to the time domain. So you can actually get it to look like a oscilloscope where it's magnitude versus time, but you're looking at the RF flowing in time down a transmission line. And in this example, Tom was showing a setup that he did where he had a piece of 75 ohm cable, a piece of 50 ohm cable, a piece of 25 ohm cable, and then a piece of open, or the end of the 25 ohm cable was open. And you can see when he did the time domain reflectometer, which is one of the modes that you can program the software into, at every one of those discontinuities there where you see the 1, 2, 3, and then finally the last one going up, those are each of the discontinuities between the different impedances of the cable. So you can actually measure, how many nanoseconds, and then knowing the velocity factor of the cable, you can actually calculate what the length of those various pieces of the cable are and where the discontinuities are. So you see where it measured the first one as 71.8 ohms, and that next one is 49 point something ohms, and the last one is 25.9 ohms. And so, if you have that old-fashioned Christmas lights where if one bulb goes out, the whole thing doesn't work, you can use your network analyzer to find that bad bulb. Tom also set up a little demonstration here where he set up a cavity filter using a cookie tin, and went through the calculations on the size of the cookie tin and so forth. And it turns out that this thing should resonate at 1.2 gigahertz, 1209 megahertz. And so he actually hooked it up to his network analyzer. And here you see the response curve of the cavity. And you see, in fact, that the cavity notch is, in fact, at close, 1210.9 megahertz. So. And so you can do all kinds of measurements. When I was doing this presentation in the real mode, then I took the MFJ and hooked it up to a dual band mobile antenna. And kind of tough with the MFJ because there's no computer interface. You can't show people what you're looking at, but as I turned the knobs, you could see the display and the meters moving around, and you could find the resonant point. And then, of course, with the vector network analyzer, you could do the same thing, and you could hook it up and and do all your measurements with the software, and then the software you could actually or display out. So this would be how hams might use the MFJ or the vector network analyzer as a one-port analyzer. You could find the resonant point of the antenna, and if it was a dual band antenna, you'd see both bands. You could see the resonant point. I think as a demo, I took an old Barker and Williamson low-pass filter that I had and did a measurement of it. You would connect the low-pass filter in between port 1 and port 2 of the analyzer, and you could see the response of the filter and show where it dropped off. I think this was an old VNWA HF filter, so I think it dropped off, just beyond 30 megahertz. I've used it. The club had a Cushcraft tri-bander antenna, an A3 that had sat around for a long time, and I think spiders and moisture and water had gotten into the traps, and so I actually used the vector network analyzer to test all the traps out, and found a couple that weren't working, and was able to take them apart, clean them up, tighten down some screws that had gotten some corrosion, and got all the traps working. So you can use it, to measure traps and all kinds of things. It's a very, very handy device. So, both the MFJ and the vector network analyzer are what's called broadband devices. So what we mean by that is there's not a lot of selectivity on the input, so you have to be cognizant of what you're doing, because there's no filtering on the input, so RF energy can get in from anywhere, from any frequency. I remember we took I'm the repeater trustee for the Central Mass 146.97 repeater up in Paxton, and we took the vector network analyzer up there, and we're trying to look at our cans up there, our cavities, and there's just so much energy up there floating around that it was really hard to get some decent measurements. We finally, using some double shielded coax cables and keeping them very short and stuff, we were able to get some really good measurements and able to tune our cavities. They happened to be very close. They just needed a small tweak, but we were able to tune them. So obviously contact information, I think everybody knows about that. I think they're still selling the SDR kits, but one of the things that Ron and I was talking about is a follow-up to this presentation that I have done, and I was going to present at the ARRL New England Convention this year, but of course because of COVID that got canceled. But I have a presentation. There's a new, pretty new device out now called the Nano VNA, and it's very similar to this vector network analyzer that I've showed in this presentation, but it's even classier. It's much smaller. It has a built-in touch display, so you can use it as a standalone device, but you can also use it with a PC or a laptop. And so what Ron and I were talking about is maybe sometime in the coming months I can do a follow-up presentation from this one of the Nano VNA. And the nice thing about the Nano VNA is where I paid $450 for that vector network analyzer I've shown here some 8 or 10 years ago. Thanks to technology and China manufacturing, you can get that Nano VNA, which covers, I believe, like 10 kilohertz to 900 megahertz for around $50. So it's quite the catch. So that's it. If anybody has questions, and that you can think of or you don't think of until later and you want to ask me, my call sign at ARRL.net or my call sign at Comcast.net will get your email to me. I'd be glad to answer any questions you might have. And that's it for now. Are there any questions that anybody has at this point that you'd like to bring up?
I guess I'll ask.
Okay, I guess not. Yeah, go ahead.
It's Roger. I have the Nano VNA H4. That's the one with a 4-inch screen. It's about $60 right now. I've been playing with it. How does that compare to the SDR kits one you showed that requires a PC?
They're very comparable, Roger. I would think from a measurement point of view, they're very similar as to what they can do. And so, you know, yeah, $50 or whatever compared to 450 is certainly a nice break. And so any of the measurements that you can do with that SDR kits one that I have, you can do with the Nano VNA as well. And accuracy and dynamic range are about the same.
Well, that's what I want to know, accuracy and dynamic range. Something else you might want to mention is the short open load calibration can be done at a distance away from the bridge. So let's say you want to measure something and you need to use a cable to reach to it. You can attach the cable to the bridge or the vector network analyzer, do your calibration, and then when you connect the device at the end of the cable, you'll get the actual measurement at the device.
Yep. So Roger is correct. Yeah, you can hook cables up. In fact, when you buy the Nano VNA, it comes with 2 small SMA to SMA cables, but you could certainly do longer ones. And you do the short open load cal at the end of the cable, right where you're going to attach your antenna or whatever your device under test does. And when it does the calibration, then it takes out all the uncertainty and unknowns within that cable, and it corrects for all of those. So the measurement that you're getting is really the measurement of the device that you're trying to measure.
Now I got a question about the MFJ.
Yeah.
What diodes are in there? I got a MFJ I'm repairing. It looks like I need to do a diodectomy.
I don't know, actually. I've never blown mine up, so I don't know what the diodes are in there.
Yeah, leave it to Ted to show up with the blown up analyzer.
Well, I'm trying to align it, and when I'm working the little pots, the R's and the S's are moving just a few ohms. I'm not getting anywhere near 0 or 255, so I figure that it's a diode problem.
Yeah, I don't know. I'll look, Ted, and I have a larger schematic. You know, I showed the schematic here in the PowerPoint, but I have a larger computer copy of that. I'll look at the schematic and I'll see if it has any nomenclature on what the diodes are.
Okay. Thank you.
Sure, no problem. Anything else? Anyone have anything else? If not, Ron, I will.
Yeah, thank you, Greg. Yeah, I mean, this was great. I think, we had over 20 people attending there, and I think, your mention of the Nano VNA, that a lot of people have picked that up just because of the price point, myself included, and are like, kind of lost with the thing when you get it, right? So
yeah, because the documentation that comes with it is like nothing. They just give you this little paper showing the menu, and if you've never used a vector network analyzer before, I can see why someone would be totally lost.
Yeah, and so I think that's probably a bit of a theme, probably with some of the younger hams who've, maybe hadn't sprung for an MFJ in the past or something, but now this thing's here for, because I think,
Yeah,
for $60,
that was the whole
you're getting
purpose of
one
my
with a battery.
that was the whole purpose of my talk that I was going to do at the convention this year on the Nano VNA, was just an introduction and to help those people who purchased one but didn't know where to start with it. And so it was basically an intro and say, okay, here's how you start, here's how you do a measurement, here's how you do a calibration, so on and so forth. So.
Well, I'm thinking if we plan to do the presentation for that in this winter, like January or February, something like that, we have enough lead time. People who are interested may even pick one up, before the presentation kind of thing. So I think that's what we're going to look to do. I did get the about the last 2/3 of the presentation recorded right after you had done the MFJ. I figured out what was going on, so I did get that recorded. So that's good. We'll be able to put that up on the site. So thanks a lot. I'm going to end the recording now.